Here I have chosen 3 more problems in real analysis. We define a set function f that takes the interval a to b, open interval, and maps it to the length b minus a raised to the 1/2 power. And we want to find the outer measure of the interval from -1 to 1. So this was a homework problem that was come up with on the spot during class when we were learning about the construction of Lebesgue outer measure. Now the way the Lebesgue outer measure is constructed is that we looked at the lengths of open intervals and took covers of sets and then defined it to be the infimum of the sum of the lengths of those intervals from that cover. Now, if you're not familiar with the construction of Lebesgue outer measure, it's a little bit complicated to explain with words without writing anything down, But this is where the motivation came from. So someone in the class asked, what happens if you redefine the set function f, where instead of taking the length of the interval, you take the square root of the length? And so it was a problem that the instructor thought was kind of interesting, I guess. So he decided to give it as a homework problem. And this is the problem. And by the way, this problem actually inspired, I think, a qualifying exam problem. It wasn't the exact one, but inspired a qualifying exam question that was on the test that I took. I believe it was problem 2. Anyway, so what does the proof say? We let epsilon be given. We're always playing with epsilon. And we decide to cover the compact interval -1 to 1 with this open interval. So it's an open interval that's just a little bit bigger than this interval here. So by epsilon that much. And then we notice that by definition, the outer measure of that interval has to be less than or equal to f of that interval there based on the definition of mu star. Again, the definition is not written up there. It's kind of in the notes. Just know that it's the usual, I believe it's called the Carathéodory construction of outer measure, but it models the same construction that the Lebesgue outer measure is, except we're using this function. But anyway, I digress. So that is less than or equal to f of that interval, and that's just the length, take the square root. So the length is 2 plus 2 epsilon, and then you take the square root of it. And then as epsilon tends towards 0, we see that the left-hand side, mu star, is independent of epsilon. So we see that mu star of this interval is less than or equal to the square root of 2. But we need to figure out what this is equal to. We can't just say that it's less than or equal to square root of 2. And if I was just doing this problem without knowing where to go, like just from, grabbing things out of thin air, I might be tempted to show that mu star is bounded below by square root of 2 as well, and show that the two are equal, actually. Mu star is equal to square root of 2. But that's just a guess. And turns out that's actually the path that you want to take here. It's just, I'm trying to explain, like, if you were doing this by yourself, this might be the thoughts that, go through your head. Okay, so how are we going to do it? Because this interval is compact, we can find a countable open subcover. And because we're on the real line, our open subcover can be written as intervals. So these are all open intervals. I label them I sub I, such that the union of those intervals covers this compact interval. And so applying the definition, we see that the sum of f of I is the same as the sum of the lengths takes the square root. So all I did was just apply a definition of f here. And then we notice that the sum of square roots is greater than or equal to the square root of sum. So I add up the lengths here and then take the square root. So it's a matter of moving the square root outward. So anyway, so I know I don't really need to explain this, but for my own sake, I'm going to do it. The sum of square roots is greater than or equal to the square root of the sum of lengths. And the sum of lengths has to be bounded below by 2. Because remember, it's a cover of the interval from -1 to 1, which has length 2. So the inside cannot be smaller than 2. And so that's what I plug in here. And because mu star has to be the infimum of over all such covers here, I know that the outer measure of this interval has to be bounded below by the square root of 2 as well, because it's the infimum, right? And so what do we have? We have mu star is bounded above and below by the square root of 2, which means it has to be equal to the square root of 2. And that's the problem. Overall, a decent problem. I think it kind of helps people get an idea of just how there's more measures out there than just the usual Lebesgue outer measure. Or I mean not. Yes, there are more outer measures out there than just the Lebesgue outer measure. And I think it's a good exercise. Problem 2. We have a family, even though I haven't really written it that way, of Lebesgue measurable functions inside the unit interval 0 to 1. I label them En. We let k be a natural number, and we define the set f to be all the points inside the unit interval, such that x belongs to k sets En. So that means that there are k sets in the family to which x belongs to. Does it have to be at least k or at most k, or just, I think it might be actually at least k. This is my also greatest struggle, is I don't really write down the problem the best. I should really work on that. It's just that when I write these problems down, and I've done this problem before, I have an idea of, what the problem says and how to prove it. But it's still no excuse. I should write down the problem right. Prove that f is Lebesgue measurable and that the sum of the measures of En is bounded below by k times the measure of f, which is this set. Now this problem isn't too hard if you know how to do it, which sounds kind of weird to say, because obviously if you know how to do something, then it shouldn't be hard. But I had an instructor, my algebra instructor, actually tell us that. He says, this problem, he would tell us, like when we had a homework problem, he says, this problem, not this one, but a different one because he's algebra. He's like, this homework problem is really, really, really hard unless you know how to do it. And I always thought that was kind of a strange statement. But after doing the problem, I kind of see what he means. Anyway, let's stop rambling and just do the problem. So what's the trick? We need to define a function f, little f, to be the sum of characteristic functions defined on En. So essentially what this function f does is that it counts the number of sets En that x belongs to. So we see that f maps the unit interval to non-negative reals. It is a measurable function. And because it's measurable, its inverse function is also measurable. Now, if you take f inverse of the interval from k to infinity, this precisely gives us the number of points belonging to at least k, or k sets, in our family. Let's read that again. F inverse k to infinity is the number of points belonging to at least k sets in our family En. Okay, that makes sense. That just comes from definition. So this set f can be rewritten as the image of k to infinity under the map f inverse. So therefore it must be measurable because f inverse is a measurable function. So that proves this part here. F is a Lebesgue measurable function. So half the problem is done already, which means that all we had to do was identify this guy. Now, for the next part, we want to figure out that the sum of measures of En is bounded below by kmf. So the integral of f, again, m is our Lebesgue measure. The integral from 0 to 1 can be rewritten as the sum of integral 0 to 1 characteristic function En. All I'm doing here is I'm putting an integral sign here, and then swapping these two. And then I write by monotone convergence theorem, and I put a question mark near it. I looked at this before recording, and it's not inherently obvious to me why monotone convergence matters here. I don't really see why I need to cite it in order to swap integral with sum. I know that there's a condition out there that says I need that, but for monotone convergence theorem, I am under the impression that you need some sort of upper bound, you know what I mean, in order for this to make sense. But maybe I just need to review MCT. But I'm pretty sure you need some upper bound, and maybe I have it, I just don't see it at the moment. But apparently when I wrote this at the time, I did see it. But whatever. This part I don't really have any problems with. But this next part I do. I don't really see why I need to define the set G. So we define the set G to be the set of all points not belonging to at least k sets En, which gives us essentially the complement of f. And what that does is that I can rewrite this integral, so all I've done is rewrite the same thing I have. But now I'm splitting this integral up into two pieces, integral over f, integral over g. And because this is non-negative, which makes sense, I don't really understand why it would, I don't see how it could possibly be negative. This tells us that this integral over here is bounded below by the sum of integral f characteristic En. But again, this is the part where I'm kind of confused by. Why do I even need to take this detour through g? Why can't I just say that this is true automatically? Because, I mean, after all, this integral is equal to this guy, and we're integrating from 0 to 1, but the set f is a subset. So why can't I just use properties of integrals to just go straight to this step here? Maybe there's a step here I'm not seeing, but it seems fairly obvious to me that I can go straight from this part to this part. But whatever. Whatever. So the measures of, if I add the sum of the measures of En, okay, let's be careful here. This should be bounded below by KMF. Okay, let's see here. You know, when I went through this before recording, I understood this pretty well. And if I just take a second here, I can see why. Because because this returns a 1 if you're in En. Essentially what this does here is it returns the measure of En intersected with f. But what's f? F is the set of x that belongs to k sets En. So there has to be like k of them, which is where this k comes from. But why measure of f? Well, DMF gives me the measure of f, which makes sense. And supposedly I have k amount of them. Because it returns a 0 if you're not inside of f. Maybe I should read this next part. F is bounded below by k on f by definition. Yeah, that makes sense. F has to be bounded below by k on f, because that's the definition of f. And f. Well, I have two f's, big F and little f. So when we're on this set here, this function has to be bounded below by k. Okay, I think I've talked myself through it. And what about this guy here? How does that make sense over here? Measures of En. Oh, because it's this, the guy. Okay, yeah. See, I knew I could understand this if I just stared at it long enough. So again, it's only an easy problem if you see this guy. If you don't see this guy here, then you kind of get stuck. Unfortunately, a lot of analysis problems I think are like that. It's really easy to get stuck. But the flip side of that is once you get that hint and you see what to do, it's really easy to get yourself unstuck. At least if you're me. All right, last problem. So, I should probably also mention, this problem was a qualifier problem. And I don't remember which year it was, but it was a couple years ago. It was within I think it was like 2017 or 28, maybe 2019. One of those 3 years, 17, 18, or 19. I remember when I prepared for this qualifier exam and wrote a bunch of problems up, I did not go past the year 2015. That's as far back as I went, because the more recent problems I want to practice. I don't want to practice super old, out-of-date problems, I guess. All right, the last one. This one I found on the internet. I thought it was a good problem to practice for the test. We let fnx be a sequence of functions where we define fnx to be e to the negative n absolute value 1 minus sine x. We want to prove that the sequence converges to 0 in measure on some given fixed interval a to b. Okay, this problem's not too bad, to be honest with you. I don't know why I chose it last. I think it's because it requires one extra thing that might not be super obvious to a student. But I like the problem. I thought it was kind of cute. We want to prove the following claim. So this is just the definition of convergence and measure to 0. We want to let epsilon be given and show that the limit here tends towards 0 in a roundabout way. So we take a closer look at what's happening inside this set. If the absolute value of fn is bounded below by epsilon, this is true if and only if e to negative n, I forgot my n here when I wrote up this problem, so I wrote an n there. Negative n, absolute value 1 minus x, is bounded below by epsilon. That's just definition. And then rearranging algebraically, we can show that we can say that 1 minus sine x is less than or equal to 1 over n log of 1 over epsilon. And remember, epsilon is fixed in this case. It's some given epsilon. So log of 1 over epsilon is some number. And the idea is that we send n toward infinity, right? Because we're taking the limit as n tends toward infinity, which means that this set here, the set of x's that satisfy this inequality, should be really small. That's what we hope to show. So we make the following observation. Sine of x is equal to 1 when x is equal to pi over 2 plus 2 pi k, where k is natural number. So this neighborhood of x values where this is satisfied has to shrink as n tends toward infinity. And we notice that there are only finitely many x's where sine x is equal to 1 in any interval that you pick. It can only be equal to 1. Sine x can only ever be equal to 1 finitely many times, because we want n to tend toward infinity, so the only, x's that satisfy this for every possible n is when these two are equal, so that you get 0. Because if this number is positive, then you can choose an n large enough where this gets smaller, and then you have a contradiction. So then we notice that there are only finitely many x's that satisfy that, which has Lebesgue measure 0. And so the union of the above neighborhoods of points that tend to 0, let me read this. The Lebesgue measure of the union of the above neighborhoods of the points tend to 0 as n tends toward infinity. Okay, so that's kind of the most important, the biggest observation here. There are only finitely many x's that satisfy that condition. So we do in fact have this limit tending towards 0. So we have convergence and measure to 0. Overall, not a really bad problem. I think these 3 problems I chose today are some of the easier type problems. Maybe even the second one might be the hardest. I don't know. It's kind of subjective a little bit. Which ones people find difficult, which ones people find challenging, but it's a matter of, how familiar you are with the problems. Anyway, those are 3 problems. Stay tuned for more real analysis.